In this last unit of the course, we're going to continue to examine distributions, but we're going to start looking at continuous models. So basically things that we measure. When we look at continuous models, the challenge here is that we can no longer list or count all the different possible outcomes. For example, last unit we talked about the probability of rolling a sum of less than 9. Okay, so we could say a 1 and a 1 is less than 9, a 1 and a 2 is less than 9, and so on and so on. We can go through, we can actually make a big list. Totally fine. But with continuous things we measure, there are an infinite number of possible values. Okay, so for example, the probability that a student will have a height less than 150. Well, even just between 149 and 150, there's an infinite number of decimals. Right? Even 149.9 to 150, there's an infinite number of decimals. You can make smaller and smaller and smaller divisions. So we can't make a table or make a list of these things. It's not possible with continuous variables. So what we're going to do instead, and what we usually do, is we create a frequency table, intervals, and then make a histogram. And from a histogram, if you connect the dots, if you will, the midpoints of each interval, which is like this are their midpoints, we often get this shape. Okay? That forms a curve. So you might recall these things as frequency polygons. What we can do is we can analyze the curve. In particular, we can analyze how much of the curve has been included. So for instance, I can say how much of the curve is here, what proportion of the curve. Well, proportion is just another way of measuring a probability. Okay? The nice thing about these curves is they always add up to 1. The area underneath them has to be 1 because all the different probabilities. So that proportion that's included in our range will be the likelihood or the proportion probability percent that we want to discuss. Okay, so let's take a look at these graphs in a little bit more depth. The graphs we're going to come across, there are some standard ones. Most of the time we're going to spend our time with is this first graph. We'll call it the standard graph. It's a symmetrical one, where the part down the middle, the left side, balances with the right side. We call this the normal curve. And if you look at populations, lots of people, and you measure their heights, it would generally form a normal curve. We have some short people way down here at the left-hand side. We have some tall people way over here at the right-hand side, but most of the people are sort of in the middle. And that's true with most things. If you measure a large enough proportion of the population, it creates this graph. But it's not the only graph. There are other ones. Okay. You could have things that are skewed, as we talked about when we looked at histograms. The negative skew, we're missing the bottom portion of this. Okay. The positive skew, we're missing the top portion of this. Maybe we had a really bad test and our average was, I don't know, 50. And most people scored between 40 and 60. And it was hardly anybody in the 70s or 80s and hardly anybody at all in the 90s. That could be an example of a positive skew. Most of the marks were low. We could have a bimodal graph. In other words, there's two common areas. Back to the idea of heights for a second. We look at heights in our class. We generally find that most female students are down here and most male students are over here. Just based on gender, there's different heights. Okay. And then you can have the exponential graph. It's kind of like an exponential curve. We won't spend very much time on this one. It's just the idea that it starts off really high and it gets smaller and smaller and smaller over time. Okay, what kind of things do we want to do with this? Well, let's start with the basic one, uniform distribution. We've talked about uniform before in terms of discrete models, rolling a dice, everything's equally as likely. Well, the same thing is true with continuous things. When we graph this curve, the curve turns out to actually be a straight line. So we'll look at an example here. We have air tanks. They're used by scuba divers and they're typically filled to a pressure of 3,000 psi, pounds per square inch. A sample of 32 tanks is shown below. Okay, let's organize the data into a frequency table starting at 295 to 297. So I'll go back to like statistics for a second here. And to be honest, with continuous data, we often combine statistics with probability. Oh, put that in the wrong spot there, sorry. Intervals and frequencies. Okay, we want to go from 295 up to 297. 299.7 up to, we're going by, it looks like, oh, that's 7. Looks like we're going by 4s here. We're supposed to be going by 2s. So 299.99 up to 3001. 3001 up to 3003. Yeah, let's find our big piece of data so we know how high to stop. I see a 3004 right off the bat, a 3005, a 3006. Looks like to be the highest piece of data to me. Okay, so we need to go up to 3006. So 3003 to 5 and 5 to 7. Okay, now, I don't have the graphing calculator for this. We can do this by hand pretty quickly. Let's find all the ones between 2095 and 97. So basically 95 and 96. So 1, 2, 95, 3, 4. There's 4 of them. 97 and 98. 97 and 98. There is 1, 2, 3, 4. 4 of those. 99s and 3000s. 1, 2, 3. I see 3 of those. 99s and 3000s. 1, 2, 3. Oh, there's one right here. I missed one. 4. Okay. 01s and 02s. 01s and 02s. 01s and 02s. There's 1, 2, 3, 4. Oh, there's 4 of those. 03s and 04s. 1, 2, 3, 4. 4 of those. Seems to be a pattern going on here. And 5s and 6s. 1, 2, 3. And then our highest piece is 4. Oh, they all have the same frequency. Okay, let's sketch the histogram that goes with this. So for B, oh sorry, this is still part A. We have PSI. We have frequency. This is my first part. We start at 295, 2995, 97, 99, 01, 03, 05, and 07. We're at the end here, okay? I ran out of room. We got 1, 2, 3, 4. Well, it turns out that when I do this one, every part is the same size. That's a uniform distribution. Each bar is the same size. The height across the top is the same. This is a uniform distribution. Okay. So, based on this organization, what can you say about the likelihood of pressure of each tank? Okay. Each PSI reading between, we start at a low of 2,995 and up to 3,007 is equally likely. And if you think about it, that's a difference of 12. So in other words, they each have a 1/12th chance of getting that specific number. And I got 112 is the difference between 3,007 minus 2,995. That's where the 12 came from. Okay, try part C. What is the probability a randomly selected tank is filled to a pressure of less than 2999? Okay, because we can't make a list of these things, okay, we're going to use intervals. So less than 2999. Now notice I didn't put equal to. It didn't say less than or equal to 2999. It just said less than 2,999 psi. So where is that in our graph? Well, 2,099, that's basically here. How much of our data is there? Well, there's 4 spots that could be in there, and each one has the same likelihood of happening. 1/12. So the probability of getting this would be 4/12, or if you will, 1/3, or 0.333. If you try part 2 of that question, more than 3,000 psi. Okay, so part 2, more than 3,000 psi. Well, how many things does that include? 3,000 psi goes from here, which is in the middle of this category, all the way to the end, all the way to 2007. So from 3,000 to 3007 is 7 different possibilities, 7 different readings, each of which is 1/12th probability. So we'll get 7/12ths. Okay. Every probability is always the same, like it's uniform. Okay. If it's not uniform, we have to approach this a totally different way, but because it's uniform, we know that each probability is the same. We just got to figure out how many different probabilities that occur. Okay, we're going to get you guys to try one. So give the video a pause, see if you can figure out what's going on here. The lifespan of a great white shark varies uniformly from 15 to 32 years. So in other words, the probability of any 1 year of living to a certain length would be 1 out of 17. I get 17 because I know the difference between 32 and 15 is 17. So for part A, what's probably the shark will live to 30? So it dies after 30. So I want to be greater than 30. What does that include? Well, based on this, they live from 30 to 32. That's 2 different things. And each has a 1 in 17 chance of living. So 2/17. Oh, sorry, you know what? I read that question wrong. I want to live specifically to 30 years. Not more than 30 years. We got to fix this. I don't want greater than 30. I want is 30. The likelihood we live specifically to 30, that specific year, that's 1/17. If it was more than 30, that's a different question. I didn't read that one carefully. Okay, probably the shark would die after 20 years. So in other words, it lives to 20 or more. So we're looking for more than 20. How many different possibilities is that? Well, from 20 to 32 is 12 possibilities. Each has 1 in 17 chance. So 12 out of 17. Okay, so that's a really brief introduction to continuous distributions. We're going to look at uniform ones today. They're pretty simple. And basically, you're doing subtracting, right? These things make a straight line. They're uniform. They're all the same probability, which allows us to solve problems pretty quickly with them. As you notice on the last question, you do have to read carefully. So live to 30 years is different than more than 30 years or less than 30 years. This was just the one specific case right there. Whereas other ones have this interval, and more than, less than, between, you have to pay attention to. Okay, some homework questions that you can try. Hopefully you can figure those out pretty straight. They're pretty straightforward, but if you're stuck, come see me and we'll go over them together.